Okay, we're back. We're going to resume where we left off. We talked about inverse functions and their relationship from a graphical standpoint, that they're reflections of each other across the line y equals x. Therefore, all points a, b on a function will be points b, a on its inverse. Okay, so we're going to look at a couple particular examples here. We got a function y equals 2x plus 6, f of x equals 2x plus 6. It's a linear, which is a line, a linear function. We're asked to find the inverse. That's what this notation is implying here. Find f inverse of x. That's how we read it. Okay. So one way of doing it would be to go back on what the closing statement over here was, that if a function contains ab, its inverse contains ba. So following that protocol, what we're going to say is, well, on this function, f of x, then clearly we know the y-intercept is 6. If we put in x equals 2, then of course we get y equals 10. So here's a point A, B. So the inverse would contain its flip-flop. Okay, so the inverse would contain 6, 0 and 10, 2. And now we could proceed to find the equation of the line containing those 2 points by going through the usual protocol of finding the slope. Okay, y2 minus y1 over x2 minus x1, and there it is right there. Okay, and then going through and the modified point slope formula and finding finding the equation of the line there. Y equals 1/2 x minus 3, and naming that as a inverse function. The inverse function is 1/2 x minus 3. If we take a look at these things collectively, here's our original function, y equals 2x plus 6. Okay, here's our inverse function, which should be the mirror image across. If we were to put in a center line here, y equals x, we'd see that the red line is the inverse, the mirror image across the line y equals x. And by no accident, their intersection is right on that line, y equals x. Okay, so let's proceed with some other examples. Okay, and we might find another way of finding the inverse of that without having to go through that modified point slope form. Okay, so uh, all along we've been suggesting that if a point AB is on a function, then its inverse is BA, then its inverse would contain BA. If we generalize that, that what we're actually doing is we're exchanging the x and y's. You know, x becomes y, y becomes x. And again, that's by no accident, because we're flipping this across the y equals x line. All right. So we're going to extend that rationale to try to find the inverse of a little bit more sophisticated function. Okay, so here we are. We got this function, y is equal to x minus 5 over x plus 2, and we're asked to find its inverse. Okay, so what we're going to do is, since I've already said it, f of x is y, so we're going to name it that way. And what we're effectively going to do is take advantage of this idea up here, that we flip the x and y's, because the inverses are flipped across the line y equals x. So here we're just going to exchange the x and y's. X becomes y, y becomes x. Okay, and that's what it gives us. But now we want to write that in function notation, or ultimately in function notation. So we have to isolate y. And to do that, again, we're going to cross multiply, in which case we get x times y plus 2, or xy plus 2x. And again, we're trying to isolate y, so we're going to exchange the 2x and the y, positionally speaking, and that's going to give us this. We're going to factor out the y from the left-hand side, okay? And then we're going to divide through by the x minus 1, and that's going to give us a expression y in terms of x, which is in fact the inverse of our original function, so we're going to show it a little respect and give it that inverse notation. So the procedure for finding the inverse of this function was to write the function y in terms of x instead of f of x, and then exchange x and y's, solve for the new y, and then replace that y with the inverse notation. Now let's take a look at these from a graphical standpoint. Okay, so here's our original function, and we're going to want to ask things about what is its domain and maybe what is its range. Okay, so from the graph, or even before we graph, we knew that x couldn't equal -2. So therefore, no surprise, there's an asymptote there, and the domain, therefore, is everything but -2. Okay? We should also see from the graph that there's also what effectively is going to be called a horizontal asymptote, where this thing is coming to settle on the line y equals 1, which is to say that the range is everything but 1. Now you're probably asking, well, how would we determine that if not from the graph? Well, we actually did that previously when dealing with functions. Okay, you should be able to return to the what we did previously, and this function you could very easily solve for the range. Okay, so you might want to recall that. Now we look at the inverse function again, which we generated already, and clearly we know that this thing is not defined at 1. So therefore, the domain here is everything but 1. All right, and then the range, again, we could find the range of this function as we did previously. Okay, or we could take a look at the picture. But we could also see that the range is everything but -2. Now, shouldn't be of a surprise here. Okay, we say functions that are inverses are exchanging x and y's. So effectively, then we say that function f, the domain of function f, is the range of its inverse, and the domain of a inverse is the range of its original function. So you notice that, and again, that's all accounting for this flip across the line y equals x, x equals y, y equals x. So if you were asked to find the domain and range of this function and its inverse, clearly we could define the domain, by just looking at it. Having the domain of that function will tell you what is the range of the inverse. Then if we take and proceed to find the inverse of this function, as stated previously in this presentation, then the domain of the inverse would effectively be the range of the original function. So that's what's stated here, and this idea will prove to be the case for all inverse functions, that the domain of a function is the range of its inverse, the range of a function is the domain of its inverse. I think we'll terminate this session here and pick up with another one momentarily.